This is the fourth lecture on Text Unit 7, which is on molecules and bonding. In this lecture, we look at the relationship between Lewis structures and molecular shape, focus of which is VSEPR theory. You should refer to your molecular shapes handout that you could download from Blackboard during this lecture. Molecular shapes are actually very important, as you'll later see in organic chemistry and biochemistry, play a critical role in the action of enzymes and in drug designs. Most Lewis structures for molecules most geometries of molecules, can be predicted with reasonable accuracy from their Lewis structures. For example, here's an easy case before we move on. All diatomic molecules are linear. 2 points make a line. Alright, now let's move on to look at molecules with more than 2 atoms. Alright, let's consider a simple 3-atom molecule, BeH2. There are 4 valence electrons, if we've seen, and the Lewis structure, there's a correct Lewis structure here, showing the 4 valence electrons as 2 bonds. Remember, the correct Lewis structure does not have an octet for the beryllium atom. Alright, so we have 2 bonds stuck to the beryllium atom, each with a pair of electrons. The electrons in this pair of bonds and in this pair repel. Negative charges repel each other. And they would, in principle, like to be as far apart as they possibly can. They can't get too far away from each other because they're both stuck to this beryllium atom. But if the molecule assumes a linear shape, the pairs are as far apart as possible, and we expect that this shape would minimize the repulsion. Right, so we predict that these 2 bonds in BeH2 will repel each other, and the molecule will assume a linear shape. Right, what we've just seen an example of is the VSEPR, or valence shell electron pair repulsion theory. In this theory, any bond, single, double, or triple, is an electron pair group and will repel other groups. And we just saw 2 bonds repel each other. Molecules with 2 bonds on the central atom and no lone pairs will always be linear. In the event we have 2 bonds on the central atom and no lone pairs, because of what we just saw. The 2 pairs will repel each other, and the molecule will assume this shape. This is the 2 pair group case that you can see on your molecular shapes handout. Alright, now as an exercise, you should draw a Lewis structure for another simple molecule, BH3, before we go on. Alright, BH3 is again another exceptional molecule. The central atom gets less than an octet. So here we have a correct Lewis structure for BH3. Now if these 3 bonds or groups all repel one another as much as they possibly can, the shape that corresponds to their greatest separation is this planar shape with angles of 120 degrees between any of the bonds. Right. This is referred to as a triangular planar or trigonal planar geometry. Note that lone pairs are also pair groups, just like bonds. Here's a Lewis structure for BCl3, for example, 3 groups on the boron. And here we see the 2 resonance structures for SO2. No formal charges have been added. Both BCl3 and SO2 have 3 pair groups on the central atom. So the sulfur has 1 bond, another bond, and a lone pair. That's 3 pair groups. Again, this Lewis structure shows formal charges for both resonance structures. Note that both resonance structures have 3 pair groups on the sulfur. You could look at either resonance structure when you're thinking about determining the shape. Since both of these molecules have 3 pair groups on the central atom, the groups in both cases will arrange themselves in a trigonal planar shape. However, as you could see from the handout, which illustrates 3 pair group cases, a planar triangular arrangement for BCl3, here A indicates a central atom and 3 outer atoms is X3. The geometry of the molecule is trigonal planar. In the case of SO2, you have 3 groups, 2 bonds and a lone pair. They are trigonal planar, as shown by this geometry. Note the notation X2E means 2 bonds and a lone pair. In the case of 2 bonds and a lone pair, if you're just talking about the shape of the molecule, not group, these 3 atoms, the shape of the molecule is actually bent. So 3 pair group cases fall into two types of geometries of molecules, planar, triangular, and bent, even though both cases have a planar triangular arrangement of groups. Continue to look at your handout. 4 groups on a central atom form a tetrahedron. Methane, CH4, is an example of the case in which all pair groups are bonds. If you make a Lewis structure for CH4, there are 4 central bonds coming from the single bonds coming from the central atom. And this is a repulsion minimizing tetrahedral geometry. All the angles between any 2 bonds are idealized angles from an idealized tetrahedron of 109.5. Now, cases in which there are 4 pair groups on a central atom fall into 3 categories. There is a 4 bonds case, which is CH4. There is a 3 bonds and lone pair case, exemplified by NH3. And a 2 bond and 2 lone pair case exemplified by water. All of these molecules have 4 groups on the central atom and a tetrahedral arrangement of groups. Only in the case where they're all bonds does that correspond to a tetrahedral molecule. If you have 1 lone pair, just looking at the 4 atoms indicates what is called a pyramidal geometry, with nitrogen at the top of the pyramid. In the case of a water molecule, where 2 of the groups are lone pairs, you just look at 3 atoms, the geometry is again nonlinear bent, although in this case of bent, we predict an idealized angle between the 2 bonds of 109.5. Again, this is another illustration of the tetrahedral groups on water. Here we see the 4 groups making a tetrahedron about the oxygen atom. But the molecule is bent, and in real life this angle is very close to the idealized tetrahedral angle, 104.5 versus 109.5. You'll see from your handout that if there are 5 pair groups on a central atom, that forms what is called a trigonal bipyramid. An example is the case of the molecule PCl5. And here are 2 ways of representing the trigonal bipyramid geometry. This is similar to what you'll see in the textbook. This triangle indicates a chlorine sticking out of the plane. This dashed line indicates a chlorine sticking into the plane. These 3 atoms and this chlorine form a trigonal planar arrangement with a bond sticking out the top and bottom. You might visualize that more clearly by looking at this picture. Here are the trigonal planar atoms here, and this bond stick out the top and bottom of the triangle. You'll note there are various 5-group cases, one all bonds. The geometry of the molecule is the same as the geometry of the groups, in this case, trigonal bipyramid. Tellurium tetrachloride has one lone pair and 4 bonds. Notice the lone pair is in the trigonal planar part of the molecule. The 4 remaining atoms attached to the central atom form what is called a distorted tetrahedral shape. If there are 2 lone pairs for 5 groups, the actual arrangement of atoms is T-shaped. And if there are 3 lone pairs, they're all in the trigonal planar part, and the arrangement of the atoms will be linear. Here's an example of a case with 5 pair groups and 1 lone pair. SF4 is a distorted tetrahedron. This is sometimes acceptably called a seesaw. Here we see the geometry with the 4 bonds and the lone pair in a trigonal pyramid arrangement. Again, if you don't look at this lone pair and just this atoms, these fluorines form the legs of the seesaw, and these fluorines form the seat. T-shaped molecules like Cl3 have 2 lone pairs on the chlorine and 3 bonds. Notice all the 5-group cases are exceptions to the octet rule. And here's an illustration of how the trigonal bipyramid shape, with 2 bonds replaced with lone pairs, produces a T-shaped molecule. Right, molecules with 6 groups on the central atom form an octahedron. And here we see SF6, for example. Octahedron has a square planar arrangement of 4 atoms around the central atom, and then a bond sticking out the top and the bottom. I hope that clears up the picture somewhat. So here's an octahedral representation similar to what you would see in the textbook. Notice there's actually some bond length information here. The distance from this sulfur to this fluorine is 156 picometers. The pico prefix has 10 to the negative 12. Here's another picture of the octahedral geometry for 6 pair groups. And again, notice that we have an octet violating Lewis structure. The octahedrid cases are the case where all the groups are bonds, in which case the geometry of the molecule is also octahedral. It looks square planar with one sticking out the top and bottom. If you replace one of the groups, the resulting shape with 5 atoms is called a square pyramid. If one of the bonds is replaced with a lone pair. If 2 bonds are replaced with lone pairs, they will be on opposite sides of the square planar part, and the shapes of the remaining atoms will be square planar. Right. This concludes the 4th lecture for Unit 7.